Hey, welcome back. This is the final exam review for Math 1610, Calculus 1. And I mainly want to focus in on limits, derivatives, and integrals. Okay, so that's what you're going to be seeing mainly. Okay, so if you don't see it in this exam review, it's not going to be on the test. Basically, there will be questions similar to the question pools that I'm giving you right here. Okay, so 2.3, we're thinking of problems like 5 to 35 odd, and then 41 to 75 odd. So you can either go to the book, or you can go to WebAssign and find similar problems. So let's go in the WebAssign for this first section and just kind of take a look-see at these guys. So you could tell which problem you're dealing with right here. Okay, so it says. And this test will be the final exam will be in WebAssign, so it's a good idea to kind of try to do these problems. Anyways, 7.2. So it's early Transcendental 7th edition, section 2.3, problem number 5. That's what that is, okay? And that's in our possible set of problems, so we can kind of go ahead and look at that guy and get some practice, okay? And that's what you do. Okay, so in the beginning, the limit problems, I mean, we had the epsilon delta stuff. I'm not going to put that on the test, but these beginning limit problems are pretty easy after everything was said and done, right? So all you were doing is basically a substitution. And that also implied, if you could do that, that the function was continuous. So something like y equals 8x plus 1 is continuous because you could do a substitution on the limit. Okay, plus 1, and evaluate the limit. And the limit will equal f of negative 2. So here is negative 16 plus 1, which is negative 15. Okay, all right. So 5 to 35 is anything difficult here? You don't know. If there is, then you stop and you do it. So maybe like this one looks hard to you or something. So I'll try number 15. Limit as x goes to 1 of x all over x squared plus 8. And the final exam will probably have about 30 questions on it. Anyways, again, this guy is continuous. It's actually continuous everywhere. Rational functions are continuous everywhere except where that denominator is equal to 0. And this guy, its denominator will never equal 0. So anyways, you could do a substitution to get your answer. So it's just going to be 1 all over 1 squared plus 8, which is 1/9, of course. So no big deal there. Let's see what else. Some trig limits, you know. So let's try, what is that problem? Number 25. Limit as x goes to 8 of the cosine of pi x over 3. These cosine functions are continuous everywhere, so you can do a substitution. This will just be 8 pi over 3. You could use your calculator to figure that out. So TI calculator, TI-84 plus or below calculators are fine. 1, 2, 3, 4, 5, 6, 7, 8 pi over 3. That's the second quadrant, so it's negative, negative 1/2. Okay. Okay. Let's see what else. You know, maybe that one looks hard, so try number 11, or it's number 34. As x goes to 0, of e to negative 8x sine pi x. Again, these guys it's a product of continuous functions. You could just do a substitution. E to the negative 8 times 0 is e to the 0 times sine of pi times 0, which is sine of 0. E to the 0 is 1. Sine of what becomes 0. Sine of 0 is just 0, so that will be equal to 0. Okay, so these are pretty easy. The harder ones were kind of like these guys, where maybe you had a removable discontinuity to deal with. So let's look at that guy, number 47. We have the limit as x goes to 0 of x all over x squared minus 8x. And if you do a substitution, you get one of those indeterminate forms, right? So if you plug in 0 on the top, you get 0. Plug in 0 on the bottom, you'll get 0 minus 0, which is 0. So you can't do a substitution here. You have to first use some algebra. So if you factor an x out of the denominator, limit as x goes to 0, the x's will cancel, and you get 1 over x minus 8. And then plugging in 0, now you can actually figure it out, right? So it's just 1 over 0 minus 8, which is minus 8, so negative 1/8. Okay. So that was one type of indeterminate. Another type is when you have to rationalize, so to speak, the numerator. It's like problem 54. So we have maybe the limit as x goes to 56 of the square root of x plus 8 minus 8 over x minus 56. And again, if you try to do a substitution here, there's issues, right? If you put it in the top, you'll get 56 plus 8 is 64, which square root of 64 is 8. 8 minus 8 is 0. You plug it in the bottom, you also get 0. Okay, so you have to do some algebra to make this work. And the algebra that makes it work is to multiply top and bottom by sort of the conjugate, right? So let's see how that worked. Instead of minus 8, you're going to go plus 8. And if you do it to the top, you have to do it to the bottom. Okay. So in the numerator, I have to kind of FOIL that out, right? So this times this, the square roots will go away, and you just have x plus 8. And then the inner and outer are opposites, so they'll add to 0. And then the last, negative 8 times 8, will be minus 64. And then downstairs, I'm not going to FOIL that out. I'm just going to leave it as it sits, because there's going to be a nice little cancellation. Okay, so here I have then the limit as x goes to 56 of x minus 56 again, all over x minus 56, and there you see the nice cancellation, right? And then square root of x plus 8, boom, boom, those are goodbyes. Limit as x goes to 56 of 1 all over the square root of x plus 8 plus 8. And finally, you can do a substitution, and it will be determined. All right, so you can put in 56, you'll get 1 over 56 plus 8 is 64, plus 8. Square root of 64 is 8. And finally, you get 1 over 16. Okay. Okay, so those kind of problems. And then we had transcendental forms as well. So problems like 41 to 75, we need to remind ourselves that the limit as x goes to 0 of sine of x over x is 1, and then the limit as x goes to 0 of 1 minus cosine x all over x is 0. Okay, so those become important in figuring these things out. So let's take a look at 67-ish. That's the limit as x goes to 0 of sine to the 8th x over x. We could rewrite that as the limit as x goes to 0 of sine x over x times sine to the 7th x. Okay. And then if you can evaluate the limit of each term and each factor in the product, then you could take the product of the limits. In other words, we could rewrite this as the limit of sine of x over x times the limit of sine to the 7th x, sine x to the 7th, so long as those limits exist. Okay? If they didn't exist, you'd have to try something else, right? But we know these work. So the first one is 1. The second one, you could do a substitution. Sine of 0 is 0. And you just end up with 0. Okay. We could try number 71. Limit as x goes to 0 of 16 minus 16 cosine x all over 8. What can we do here? So we want to get it into this Well, do we even need to do that? This is just a simple one. This is just a substitution. It kind of looks like the 1 minus cosine x over x, but there's no x in the denominator, and you could do a substitution, right? So you could plug in 0 for x. You'll get 16 minus 16 times 1 all over 8, which is just going to be 0. So that's kind of a tricky question. Getting carried away with these problems. I feel like we should go on to the next section. Let me do one more. I apologize. This is overkill, I think. Limit as t goes to 0 of sine of 8t over 7t. So the deal with this one, limit as t goes to 0, you need sine of 8t over 8t. Okay, sine of 8t all over 8t. And you could get that by kind of multiplying in a clever way. You could factor out the 1/7 for one thing, and then you can multiply by 8 over 8, which is kind of what's going on here. Okay. At the end, then you could factor out the 8/7, and then you just have the limit of sine of 8t all over 8t. And then this limit part is just 1. Okay. And you just end up with 8/7. So you see, if going in reverse, you could kind of see it a little better. 8 over 1, the 8 will cancel with this 8, and you're just left with the 7t in the denominator. So you have to be kind of clever with multiplying and canceling things out to get it to work. Okay, so that's good. Okay, so make sure you can do limits of that type. 2.5, then I'm looking at problems like 37 to 51 odd. And these are the infinite limit types. Okay. So let's carry on with that material. So 2.5-ish. Here's 2.5. And expand all. So 37-ish. This is 9. Yeah, okay, so here we go. These one-sided limits. Sorry, just 1 second. Okay, here's a nice one I like. I have no idea what that number means on there. 2.5, 508. I'm just going to go with the book on these ones. So 37 to 51. But looking at this, I'm in the wrong section. 2.5, 37. Okay, so let's look at 37. So limit as x goes to 2 from the right of all over x minus 2. Okay, so these types you'll have are something like L over 0. So whenever you have L over 0 types, they'll either be plus or minus infinity. It's going to be one or the other. Okay. To figure out which one it is, you do a test value. Okay, so I'm coming in the 2 from the positive side, so I'm thinking numbers like 2.1. Okay, and then you plug that into this expression here and figure out if it's positive or negative. So it'll be 2.1 all over 2.1 minus 2 is positive, so it'll end up being positive infinity. Okay. So that problem to the right there in WebAssign, whatever number that means, the limit as x goes to negative 8 from the right of 1 over x plus 8. How did that work then? So again, this is L over 0, so you know it's either positive or negative infinity. Here's negative 8. I want to come in from the right, the positives, and so I'll have something like negative 7.9. If you plug that in, you'll get 1 over negative 7.9 plus 8 is positive. So positive over positive is positive infinity. Okay. Let's look at that number 20 in WebAssign here. The limit as x goes to 8 from the left of negative 8 all over x minus 8 squared. again, that's L over 0. And we're coming in to 8 from the negative side this time. So test value would be something like 7.9. If the numerator is negative, the denominator will always be positive because it's squared. Sorry. So your answer is going to be negative over positive, which is negative. So you end up with negative infinity. Okay. All right, so let's look at some other ones here. 41 from the book. You have the limit as x goes to 0 from the left of 1 plus 1 over x. Okay, and we had all these other forms. So L plus infinity is infinity. L minus infinity is minus infinity. Okay, so in this case, we have L plus something, and we have to figure out what that something is. So in particular, the limit as 1 over x as x goes to 0 from the left. So this time, here's 0. I'm coming in from the negative side. So I'm taking test values like negative 0.1. That'll be positive over negative. So this will be negative infinity. So it's L minus infinity. And of course, that will be minus infinity. Okay. All right. Let's see if there's any other ones in the homework that really are nice in that span of problems. Not getting any nice ones here. 4 plus 4. I mean, that one's an L over infinity too. Let's try that one. So this is number 53 and 2.5. Well, that's out of my range. I only want to go up to 51. Let's look at 50 there. Looks pretty weird. 50. Limit as x goes to 0 from the right of e to the negative 0.8x sine x. In this case, then, you have, well, this isn't even the type, right? This is just plugging in. So you'll have e to the 0, which is 1, times sine of 0, which is 0. That will just be 0. So that wasn't even an infinite thing. How about this guy? So number 43. It's more along in our wheelhouse. Negative 9 from the left of x squared plus 8 all over x plus 9. So this guy here, I'm coming in from the so negative 9. I'm coming in from the negative side. In particular, I'm worried about this part, right? Because this is going to be L plus something. And that something is going to determine what happens. So coming into negative 9 from that direction, I'm thinking of things like negative 9.1. And if I plug that into the thing I just circled right there, I'll get a positive over a negative, which is negative. So it's going to be L plus negative infinity, which will be negative infinity. Okay. Let's go ahead and look at one of those weird trig ones. Okay, so limit, this is number 46. The limit as x goes to pi over 2 from the right of negative 8 over cosine x. So in this case, you could maybe do a picture is better than the table. Like before I was doing the little tables for the test values. Note that this is L over 0, so it's either going to be plus or minus infinity. Anyways, cosine looks like this. I'm coming in from the positive side to pi over 2. And pi over 2 is right here. So the cosine values, these kind of output values, will all be negative, right, coming in there. So you'll have a negative over cosine of something that is coming in from the left, which will produce a negative, so that will end up being positive infinity, plus infinity. Okay. Or you could just do a test value in your calculator, something a little above pi over 2, but not too far above pi over 2. So remember, pi over 2 is like 1.5 something, so you want to pick in radians like 2, okay? Cosine of 2. Anyways, I think that's pretty good for 2.5. 3.2, we introduce the derivative. In 3.1, we do the kind of the technical definition with regards to limits. Then 3.2, we dive into the derivative, basic derivative formulas. And in 3.2, I'll be considering problems like 7 to 57 odd. Okay, so let me look in the book. So I personally, I think the best place is just go to the book and read in there. But it's nice to have you should be getting plenty of experience with WebAssign if you're doing your homework. Anyways, 7 to 57. So finding derivatives. Let's look at number 17, where we have f of t is negative 3t squared plus 2t minus 4. So these are just power rules. So be negative 3 times 2t plus 2 times 1, and then 0. So negative 6t plus 2. Okay, so you should know how to do that. You should know how to do kind of the trickier ones. Like, for example, I don't know, 29, y equals 6 all over 5x cubed. You could rewrite this as 6 all over 125 x cubed, and then you could rewrite that as 6 over 125 x cubed. Okay? So its derivative would be 6 over 125 times 3x squared, which of course will just be, whoops, this is negative, so negative 3x to the negative 4. Sorry. So that would be negative 18 all over 125 times x to the negative 4. And then, write it negative 18 all over 125 x to the 4th. Okay, get rid of those negative exponents when practical. Trig derivatives, you should know all your trig derivatives. You should be able to do the exponential ones, so like 25. You have y equals 1/2 e to the x minus 3 sine x. So y prime. Derivative of e to the x is just e to the x. Minus derivative sine is just cosine. You should be able to do things that kind of look like quotient rules but aren't. Okay, so things like f of x equals x cubed minus 3x squared plus 4. All over x squared. Don't do the quotient rule if you don't have to. Okay, you just rewrite this as x, x cubed over x minus 3 plus 4x to the negative 2, and then do the derivative. Okay. So it'd be 1 minus 8x to the negative 3 if you wish. So 1 minus 8 all over x cubed. Okay. Right, so derivatives, good stuff. Make sure if you get like a square root, you convert it to an exponent, like 51. Maybe I'm beating this to death now. F of x is a square root of x minus 6 cube root of x. Okay. So rewrite it, right? So it's x to the 1/2 minus 6x to the 1/3. And then take the derivative using power rule. So this would be 1/2 x to the negative 1/2 minus 6 times 1/3 x to the negative 2/3. And then you could simplify 1 all over 2 root x if you want, or just x to the 1/2 minus 2 all over x to the 2/3. Okay. Okay, so problems like that are fair game. That's 3.2. 3.3 then gets into the product rule and the quotient rule. So 3.3, we're looking at problems like 5 to 35 odd, and then 43 to 59 odd. And let's see, 3.3, where are you? So product rule and quotient rule. So product rule is like 1 d2 plus 2 d1. Quotient rule is low d high minus high d low. And along with that comes then the derivatives of all of the trig functions. So you should know all 6 derivatives now at this point. Let's take a look. So let's try number 13. No, let's do a product rule first. So number 9, f of x equals e to the x times cosine x. Okay, so f prime. Leave one of them alone, so leave e to the x alone, and then take the derivative of the other, plus take the derivative of the one you did not take the derivative of. And unfortunately, the derivative of e to the x is just e to the x, so it doesn't look like I did anything, but I did. Simplify that a bit. Negative e to the x sine x plus e to the x cosine x. Okay. Also need to know quotient rule. So let's look at a quotient rule. And let's look at 35. So we have f of x equals 3x minus 1 all over the square root of x. So you could just split this up. Let's do the quotient rule when in Rome. So low, which is x to the 1/2, d high, which is 3, minus high, 3x minus 1, d low, which would be 1/2 x to the negative 1/2, all over the low squared. Square root of x squared is just x. Okay. I'm going to clean up the top by multiplying through by 2x to the 1/2. Okay. 2x to the 1/2. So this times this will give me 6x to the 1/2 plus 1/2 is just 6x minus 3x minus 1. This times this part of it will be just 1, right? Which is why I did it that way. And then downstairs I have 2x to the 1 plus 1/2 is 3/2. And then you can simplify the top, 6x minus 3x plus 1 over 2x to the 3/2. So it'll be 3x plus 1 all over 2x to the 3/2. Okay. Let's go into WebAssign and see if they have anything unusual that we can look at for quotient rules and product rules. Okay. This is section 3.3. There's a product rule, there's a quotient rule. Let's do that one for the quotient rule. So f of x equals x all over x minus 8. So f prime of x, you do have to do a quotient rule on this one. Low times the derivative of the high minus high times the derivative of the low. Whoops, the derivative of the low is 1. Sorry, got carried away there. All over the low squared. And then that'll be x minus 8 minus x all over x minus 8 squared. That'll just be negative 8 over x minus 8 squared. Okay, so you just randomly kind of go through and find problems to work on. That one looks annoying. That's like the one we just did. Just we'll do one more product rule and then we'll go on to the next section. So this looks like it's number 43. And it has some trig stuff in there. So t to the 8th sine of t. So f prime of t, leave the t to the 8th alone, take the derivative of sine. And then the derivative to the 8th is 8t to the 7th, and leave sine alone. Okay, that's pretty much all there is to it. Okay, so let's make sure you know all the derivatives of the weird ones. So, here's number 48. Y equals e to the x minus cotan x. So you should know the derivative of cotan. Y prime is e to the x minus negative cosecant squared x. And then that'll just be e to the x plus cosecant squared x. Okay, great. So, quotient rule, product rule. Then the last section I want to look at in chapter 3 is the chain rule. And 3.6 we're looking at 17 to 41 odd. So, let's look at number, I guess, 15, start there. Y equals 3 times 4 minus 9x to the 5 6. Okay, so y prime, you kind of take the derivative of the outer part and then tack on the derivative of the guts, right? So it'll be, bring down the power, 3 times 5 6 times 4 minus 9x to the 5 6 minus 6 6, which is negative 1 6, and then times the derivative of the guts, which should be negative 9. Okay, so I would get, I have to do a bit of simplification here. This will be 2, 3, negative 9 times 5 is negative 45, all over 2 times 4 minus 9x to the 1 6. Okay. Let's look at another. So, I like these, like 27. We have y equals x all over the square root of x squared plus 1. Okay, so this is a quotient rule and chain rule. So you may want to rewrite it as x over x squared plus 1 to the 1/2. So you'll have low d high, x squared plus 1 to the 1/2 times the derivative of the high minus high times the derivative of the low, 1/2 x squared plus 1 to the negative 1/2 times 2x all over the low squared. X squared plus 1 to the 1/2 squared is just x squared plus 1 to the first power. I want to get rid of, look, if you rewrite it like x squared plus 1 to the 1/2, then minus the 2 will cancel the 1/2. You'll have x squared all over x squared plus 1 to the 1/2 all over x squared plus 1. You kind of see here what you need to do. You need to get rid of this fraction in the numerator here, this thing. So that's what you multiply by. That's how I know what to multiply top and bottom by. Okay, so I'm going to multiply top and bottom by x squared plus 1 to the 1/2. And so I distribute in the top. So this times this, the exponents will add to give you 1. So you just get x squared plus 1 to the 1, which is x squared plus 1. This times this, the denominator will cancel, and you just get x squared. And then this times this, you add the exponents. So it'll be x squared plus 1 to the 1 plus 1/2, which is 3/2. And then these guys will cancel, and you get 1 all over x squared plus 1 to the 3/2. Okay. So definitely you'll see something like that. Trig versions of this dilemma. Let's look at 37. Yes, y equals sine of pi x squared. Okay, so the squared is inside the sine. And how do we do this? So one way I taught you to do it is kind of work in terms of inner to outer. So the innermost part is pi x, and then you could say v is u squared, and then you could say y is sine of v. And then to get the derivative, you just take the derivative of each one of these parts and then multiply them together. So y prime will be cosine of v times 2u times pi. And then it's just a matter of back subbing. Okay, so cosine of u squared times 2u times pi, and then u is pi x. So this will be cosine of pi x squared times 2 times pi x times pi. And then finally you'll get 2 pi squared x times cosine of pi x squared. Okay. So let's do one more chain rule with trigs, and then there's also natural logs in here too. Okay. I just want to make sure that's right. Yeah, it looks okay. Sure, let's just move on to the logarithm ones then. There's exponential ones in there, of course, like 57. Y equals e to the 5x. So y prime gives you right back e to the 5x, but then times the derivative of the guts, which is 5. So that's 5e to the 5x. There's also logarithms in here. Sometimes it's easier to expand the logarithms and then take the derivative. Select number 79. You have the y equals ln of x times the square root of x squared minus 1. Okay. So what I would do is rewrite it as ln of x plus ln of x squared minus 1 to the 1/2, and then rewrite that as ln of x plus 1/2 ln of x squared minus 1, and then take the derivative. That'd be a little easier. Okay, so y prime, ln of x, derivative is 1 over x plus 1/2 ln of x squared minus 1, so it's 1 all over the x squared minus 1 part, and then times the derivative of x squared minus 1, which is 2x. So y prime should be 1 over x, 1/2, and the 2 will cancel, plus x over x squared minus 1. Okay, so that will do 3.4. And then 3.5, we have implicit differentiation. So that's where you're always tacking on the y prime part. So I'm looking at problems like 5 to 25 odd. Where are you? 25 odd. So like number, let's look at 15. That one looks kind of hard. xe to the y minus 10x plus 3y is 0. Okay. So you kind of just work as usual, and then if you take the derivative of a y variable, you have to tack on a y prime. Okay, so this first part requires a product rule. So leave x alone, and then the derivative of e to the y is e to the y. But then you have to tack on a y prime. Plus, now take the derivative of x, which is 1, and leave e to the y alone. Then minus the derivative of 10x is just negative 10. And then plus the derivative of 3y is 3, derivative of y is 1, but then you always have to tack on y prime. Okay. Then I want to get all the y prime stuff together. So xe to the y prime, plus 3y prime equals 10 minus e to the y. Okay, and then factor out the y prime. So you get xe to the y plus 3 equals 10 minus e to the y. And then finally solve. Y prime is 10 minus e to the y all over x e to the y plus 3. Okay. So problems like that. 3.5. 3.6 gives us derivatives of inverse functions. And we're looking at problems like 17 to 41 odd. And we have some more formulas that we kind of need to know. So in particular, I expect you to know the derivative with respect to x of sine inverse, derivative with respect to u, so you can use a chain rule of u, is going to be 1 all over the square root of 1 minus u squared times the derivative of u with respect to x. And then the derivative with respect to u of tan inverse, or arctan if you would rather, of u is 1 all over 1 plus u squared times the derivative of u with respect to x. So you have to have those memorized. Of course, there's no formulas given on the test. So let's take a look at some of these. Okay, so what did I say? 17 to 41. Let's look at 23. So it looks like we're going to end up with a quotient rule on this one. So I have arc sine of 3x all over x. Okay. So g prime of x is going to be low times the derivative of the high, which will be 1 all over the square root of 1 minus 9x squared times the derivative of 3x, which is 3. minus, so that's low d high minus high d low, arc sine of 3x times 1, all over the low squared. And for this problem, I think they'll just let you kind of write it with a complex fraction. So 3x all over 1 minus 9x squared minus arc sine of 3x all over x squared. If you're worried, you can multiply by 1 minus 9x squared, square root of 1 minus 9x squared on top and bottom. You'll get 3x minus the square root of 1 minus 9x squared times arc sine of 3x all over x squared times the square root of 1 minus 9x squared. Okay. But I think you're allowed in WebAssign to just leave it like this. Okay, that's 3.6, 4.5. So I'm going to fast forward all the way through. Chapter 4 was applications of derivatives, so some high-powered theorems in there, Rolle's theorem, mean value theorem, graphing equations, finding maxes and mins. So to maximize a function, you take its derivative, set it equal to 0, find the critical numbers, and the critical numbers turn out usually to be where the maximums or minimums are located. In 4.5, we had infinite limits, so I want to focus in on that section. So I'm really interested in limits, derivatives, and integrals. Okay, 17 to 41 odd, and we have limits to infinity. Okay, so these are pretty simple. It's like you're just circling the high degree terms and kind of figuring it out from there. But one factoid, some facts to remember, of course, the limit of x to pretty much any power that's positive all over, or wait a second, sorry, the limit of some constant all over x to any positive power as x goes to infinity is always going to be 0. Okay, so we kind of use that fact to develop rules of these limits. Limit as x goes to infinity of e to the negative x. You guys remember that? That negative x is going to make it be like 1 over e to the x. If you're putting in like 10, 100, 1,000, it'd be 1 over e to the 10, 1 over e to the 100, 1 over e to the 1,000. It's going to go to 0. Okay. So likewise, the limit as x goes to negative infinity of e to the positive x, then if you're plugging in numbers like negative 10, it'll have the same kind of end behavior. Anyways, let's take a look at some of these. So for example, 21, you have the limit as x goes to negative infinity of 2x squared plus x all over 6x cubed plus 2x squared plus x. Okay. So when you have these kinds of forms, you can just pick off the high degree terms in the numerator and denominator and look at that resulting limit. Okay. So this will be limit as x goes to negative infinity of 2x squared all over 6x cubed. And then that will be the limit as x goes to negative infinity of, I guess, just 1 all over 3x. Seem right for some reason. And then that's L over 0 form, which will just be 0. Okay. So basically, if you have L over 0, which is basically this form, or sorry, L over infinity, Jesus, that'll be 0. Okay, L over 0 is either positive or negative infinity. So this guy was L over negative infinity. It's 0. L over plus or minus infinity is always going to be 0. Okay. Let's look at one of these funny ones, like 27. Okay. So we have the limit as x goes to negative infinity of 2x plus 1 all over the square root of x squared minus x. Okay, so we can plot, we can pick off the high degree parts, but got to be a little careful this time. Infinity, we have 2x over the square root of x squared. The square root of x squared is not x, right? It's absolute value x. And absolute value x is negative x if x is less than 0, positive x if x is greater than or equal to 0, right? Okay, so in our direction, going to negative infinity, we're thinking x less than 0. So I can replace square root of x squared with negative x, and then this will just be the limit of negative 2, which of course is just negative 2. Okay, so those are always weird. Sure, let's try one like 19. Limit as x goes to infinity of 7x plus 6 all over 9x minus 4. Okay, so that would be just picking off the high degree parts. It's the limit as x goes to infinity of 7x over 9x, which of course is the limit as x goes to infinity of 7/9, which of course is just 7/9. Okay. And then of course there's ones where the numerator's degree exceeds the denominator's degree, like 15 part C. We'll just do this last one and move on. Limit as x goes to infinity of 5 minus 2x to the 3/2 all over 3x minus 4. Okay, so the high degree terms are right here and right here. And then we could rewrite our limit. So x goes to infinity. Negative 2x to the 3/2 all over 3x. That's the limit as x goes to infinity. Negative 2/3 x to the 3/2 minus 2/2 is x to the 1/2. And then that thing is going to negative infinity. So you could, if you need to, you could always do like a table. It's going to be either positive or negative infinity. If the degree of the numerator is higher than the degree of the denominator. But if you're putting in numbers like 10 squared, and then 100 squared, and then 1,000 squared, the result is going to be negative 2/3 times 10 squared to the 1/2 is just 10. And then negative 2/3 times 100. So it looks like it's getting really big negative. So it's going to negative infinity. Okay, so enough of that. Then the last is just chapter 5 stuff. It's just integral, 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 integral. Starting with 5.1, which gave you basic rules for finding indefinite integrals. So we're looking at problems like 11 to 35 odd. And so basic problems where you need to rewrite them. So like number 13, integral of 1 over x square root of x dx. You could rewrite that as 1 all over x to the 1 times x to the 1/2 is x to the 3/2. And then you could rewrite that and use the product of the power rule. Okay. So you add 1 to the old exponent, negative 3/2 plus 2/2 is negative 1/2, and then multiply by its reciprocal. It's negative 2 plus c. And if you want, you rewrite it negative 2 over square root x plus c. So any variation on that theme you should be able to handle. Let's look at 23. I like these kind of problems. X plus 6 all over the square root of x dx. Okay, so you could butterfly that thing, split it into two fractions. X over square root of x plus 6 over square root x dx. Simplify each and then use power rule. That'll be x to the 1/2 plus 6x to the negative 1/2 dx. And then that'll be x to the 1/2 plus 2/2 is 3/2 times 2/3 plus 6x to the now 1/2 times 2 plus c. And that would be 2/3 x to the 3/2 plus 12 x to the 1/2 plus c. Okay. So basically just antiderivatives. Can you figure out antiderivatives? Then we kind of connected this antiderivative to the idea of area, and that led us to the fundamental theorem of calculus, which basically said you can figure out the area underneath a graph by evaluating the antiderivatives at the endpoints of the interval in question. So that takes us to 5.4. So I'm going to skip all the hardcore theoretical stuff with the summations. If you're ever going to become a calc teacher, you definitely want to know how to do all that stuff. If you want to go to grad school and mathematics or something, you would definitely have to know how to do all that junk. But we'll presume that most of you aren't going to go there. So let's take a look at sorry, one second. Okay, anyways, so 5.4, yeah, so now we're talking about area underneath curves. Instead of indefinite integrals, we have definite integrals, and we're evaluating them, okay? So, for example, like number, let's look at number 19. It's like an interesting one. See, at least, so I'm going from -1 to 0, and I have t to the 1/3 minus t to the 2/3 dt, right? Okay, so I got to find the antiderivatives first. So this is going to be t to the 1/3 plus 3/3 is 4/3, and then times 3/4 in front, minus t to the 2/3 plus 3/3 is 5/3 times 3/5, and then evaluate from -1 to 0. Okay, so when you do the evaluation, you have to plug in the top number first, and then you plug in the bottom number. Okay, so you start with the one I just circled in red. So that would be 3/4 times 0 to the 4/3 minus 3/5 times 0 to the 5/3 minus, and then I have 3/4 times -1 to the 4/3 minus 3/5 times -1 to the 5/3. And the first part, those are just zeros, 0 minus 0. And then the second part, -1 to the 4/3. What is that? Well, it's -1 to the 4th, and then the cube root of that. -1 to the 4th is +1, and then the cube root of 1 is just 1. So this is 3/4 times 1 minus 3/5. -1 to the 5/3. So -1 to the 5/3 is the same as -1 to the 5th to the 1/3. -1 to the 5th is -1, and then the cube root of -1, believe it or not, is -1. Okay, so I have -3/4 plus 3/5, and then multiply top and bottom here by 5, finding common denominators, here by 4. So I get -15/20 plus 12/20, which is -27/20. 10, 15, 20, 27, 27, sounds good. Okay. Okay, so yeah, problems like that. 5.5, then I believe we get into the substitution problems, and I'm thinking of questions like 9 to 27 odd, and then 33 to 53 odd, and then 65 to 81 odd. Okay. So 5.5 is all about the substitution method. These are usually pretty straightforward, but then they have some curveballs in there. Anyways, let's look at, I guess, number 19. So you have 7x all over 1 minus x squared cubed dx. Okay. So I do u sub for this stuff in the parentheses, the 1 minus x squared, and then du is -2x dx, and then dx is negative du over 2x. Okay, so I have the integral of 7x all over u cubed times -du over 2x. That'll be 7/2. The x's will cancel, and there's a negative there. Don't forget that as well. -7/2 integral du over u cubed, in other words, u to the negative 3 du. And then use power rule, back sub. Negative 7/2 u now to the negative 2 divided by negative 2. Let's see. Negative, negative, positive 7/4 u squared plus c. And then we get 7 all over 4 times 1 minus x squared plus c. Okay, so substitution. Let's look at one of the trig versions. Okay, so here's 41. We have the integral of sine of 2x cosine 2x dx. There are some trig formulas you can use to rewrite this. I'm just going to do a u sub though for sine of 2x and see what happens. So du would be cosine 2x times the derivative of 2x, which is 2 dx. And solve for dx, which is du all over 2 cosine of 2x. So we end up with the integral of u times cosine of 2x times du all over 2 cosine 2x. Okay, so the cosine of 2x is cancel. You can factor out the 1/2 and you get u du. Then it's just power rule and back sub. So you get 1/2 u squared over 2 plus c. And then that equals 1/4 times sine of 2x squared plus c. And we have to worry about weird ones like 65, where the u sub doesn't quite work. Right? So if you let u equal the x plus 6, du will be just plain old dx. And then there's an issue, right? So if you tried to do your sub, you couldn't get rid of the x. So what you do is use this formula to get rid of the x stuff. So we have x equals u minus 6. So this would be the integral of u minus 6 times u to the 1/2 du. And then you still have to distribute, right? So you have to go boom, boom. So that'll be integral of u now to the 3/2 minus 6u to the 1/2 du. And then it's just power rule. Okay, so you get u to the 5/2 times 2/5 minus 6u to the 3/2 times 2/3, and then plus c. And you get 2/5 times u, which is x plus 6, to the 5/2 minus 3 goes in the 6 2 times, so 4 times x plus 6 to the 3/2, and then plus 6. So there's always these weird ones where the u sub doesn't quite work out. So expect, something like that can be on the test. And finally, then evaluating u substitutions. I gave you 2 different methods in the video. I like just dropping the limits of the integral and then at the very end doing a back sub. So let's look at something like 81. I have the integral from 3 to 4 of 4x e to the x squared dx. Okay, so I have u. I'm going to make that the exponent there, the x squared. Du is 2x dx, and then dx is du over 2x. Okay. So with this method, I just completely drop the limits on the integral and wait until the end to put them back in. So I'll have 4x e to the u times dx, which is now du over 2x. Okay. I can factor out a 4 over 2, which is the same as 2. And then I have the x's canceling, which is good. That's what I need. And then I have e to the u du. Okay. The integral of e to the u is just e to the u. Let's see. And then I can, sorry, my ear is itching. Then I can back sub 2e to the x. Whoops, and this is the part where I screwed up. There's no plus c when you do a definite integral. I'm just forgetting that I have to evaluate. Okay, so it's 2e to the x squared. And then I remind myself, okay, I have to put the 3 and the 4 back in. Okay, so you can't just put 3 and 4 in for u. That won't work. Okay, so this will end up being 2e to the 16 minus 2e to the 9th, whatever that turns out to be. If you need a decimal or something, put it in your calculator and get a decimal. Okay. Okay, so that's substitution stuff. Then we'll skip the numerical analysis, just leave that for homework, and go into 5.7, which is the logarithm stuff. So I'm thinking of problems like 5 to 41 odd. And let's take a look. So I have, let's try 13. That looks interesting. X squared minus 7 all over x 7x. You could do long division here. You could just kind of split them up by doing your butterfly. So I have x squared over 7x, which is just x over 7, minus 7 over 7x, which is just 1 over x dx. Okay, let's make sure x squared over 7x is x over 7. And then negative 7 over 7x is just negative 1 over x. So yeah, those are right. And then go ahead and integrate those. So I'll have x squared over 7 times 2 is 14. Minus 1 over x. What's the integral of 1 over x, people? Okay, so ln absolute value x. Right? Okay, and then plus some constant. All right, let's try number 19. Okay, so here I got to do long division first. The denominator's degree is less than the numerator. So I'll go x minus 3 into the x cubed minus 3x squared. And I like to use placeholders, so plus 0x's plus 5. You don't have to, but it just helps line everything up when you go to do your subtractions. So I asked myself, what times x is x cubed? So x squared times x. So I get x cubed minus 3x squared, and then subtract. So both of those are 0, and then plus 0x, so, and then plus 5. So there's really nothing left to do. It really hurts. That did not turn out to be very interesting. So this is actually equal to the integral of x squared plus 5 all over x minus 3 dx. If you're unsure, you can always find a common denominator and show that it's still equal to the same thing. So x squared all over x minus 3, top and bottom, x minus 3 plus 5 all over x minus 3. And you see you get, yeah, x cubed minus 3x squared plus 5 all over x minus 3. If you find a common denominator and then combine the numerators of the common denominator, you get back to where you started. So that worked. It's just that division was a bit unusual. Okay, once you're there, then you can integrate both parts. So this would be x cubed over 3 plus 5 ln absolute value x minus 3. Let's see. That wasn't very eventful. Let's look at another one. I don't know. Let's look at one maybe that works out a little nicer, right? Let's look at 17. No. Yeah, sure. Let's look at 17. So this one is the integral of x squared minus 3x plus 2 all over x plus 1 dx. So x squared minus 3x plus 2 divided by x plus 1. This will be more traditional, probably more like the one I'll put on the test. So x times x is x squared, x times 1 is plus x. So you have to know how to do long division for the test. Negative 3x minus x is negative 4x. Bring down the 2. So what times x is negative 4x? So negative 4. X minus 4. Then I have to subtract everything. So that would be 6. So my integral becomes x minus 4 plus 6 over x plus 1 dx. And then that will just be x squared over 2 minus 4x plus 6 ln absolute value x plus 1 plus c. Let's just do a simple one. We're going to put a simple one on there. 3 all over 5 minus 2x dx. So my point on this one is you can't just write 3 ln absolute value of 5 minus 2x. That won't work. Okay, you could do that for simple ones like this, or this one. Okay, that's just 5 ln of x minus 3, but you can't do that here. Yeah, look at the u sub. Differential is negative 2 dx. Dx is negative du over 2. So when I do my sub, I'll have 3 over u, and then there'll be this negative 1/2 floating around. Okay, that changes it. That's why it's not just 3 ln of absolute value 5 minus 2x, right? It's negative 3/2 ln blah blah blah. So this will be du over u, and then that'll be negative 3/2 ln absolute value of u plus c, and then back subbing negative 3/2 ln absolute value of 5 minus 2x plus c. Okay, the last section I'm going to put in there is 5.8. I'm not going to put the hyperbolic functions in on this guy, on this test. 3 to the 41 odd. 5.8 inverse trig formulas that you need to know. The integral of du all over the square root of a squared minus u squared, is arc sine, or if you'd rather, sine inverse of u all over a plus c. And then the integral of du all over a squared plus u squared is 1 all over a arc tan of u all over a plus c. Okay. And so you have to have those memorized. And let's take a look. Okay, so I guess number 7. 1 all over the square root of 1 minus x plus 1 squared dx. Okay, so this obviously has the sine inverse form. In this case, the a is just 1, but the u is x plus 1. Okay, so the dx will become du. So here I'll have the integral of 1 all over the square root of 1 minus u squared times just du. And then that'll be sine inverse of u all over a. A is just 1. Let's see. And so that will be sine inverse of x plus 1 plus c. Okay. Let's do a tan version. So number 13. We have e to the 2x all over 4 plus e to the 4x. So this is a tan inverse, but it's just kind of disguised. You can notice if you rewrite it, e to the 4x is just e to the 2x squared. Okay, so if you let your u be e to the 2x, you kind of have it. A will be 2, u equals e to the 2x, and then the differential of e to the 2x is e to the 2x times the derivative of 2x, which is 2 dx. And then dx will be du all over 2e to the 2x. Okay, so get the integral of e to the 2x all over 4 plus u squared times du all over 2e to the 2x. And those e to the 2x's are gone now. So yay, goodbye, goodbye. You can factor out 1/2. And then we have our nice inverse tangent formula, right? So it's just the 1 plus u squared, a squared plus u squared, where a is 2. So this will be 1/2 times 1 all over a times tan inverse of u all over a. Let's see. So that'll be 1/4 tan inverse of u, which is e to the 2x all over 2 plus c. Okay, so just limits, derivatives, and integrals. That's pretty much all you're looking at for my final exam. And thanks for watching. Thanks for participating in my class. And we'll see you next year, hopefully. Okay? Have a good day.